I thank you all for watching my videos. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We now discuss the solution of a problem from the question paper CSIR National Eligibility Test held in the month of June 2023. This question is from the section Algebra broadly, but it is a problem from group theory, and it is related to P groups. And in this problem, the groups of order p to the power of 6 are discussed. This question is from the part B, which is a multiple choice question. It carries 3 marks. Its question ID is 704039. This question is suitable for all these examinations. Right. The given question is, let P be a prime number, let G be a group such that for each G belongs to capital G, small g belongs to capital G, there exists a natural number small n such that G power P power n is 1, where 1 is the identity of G. Which of the following statements is false? There is a stress on false. That means out of the 4 statements that are given to you in the options, one of them is false and the remaining 3 are true, and you have to find out that false statement. We are given 4 options. Option 1, if order of G is P power 6, then G has a subgroup of index P square. Option 2, if order of G is equal to P to the power of 6, then G has at least 5 normal subgroups. Option 3, center of G can be infinite. Option 4, there exists a group G with order of G is equal to P to the power of 6 such that G has exactly 6 normal subgroups. Right. We now discuss the solution of the problem in detail. We have a prime number P given a group G with the property for each small g belongs to capital G, there exists a natural number small n such that G power P power n is equal to 1, that is the identity of the group G. Right. And a group G with this property is called a P group. And a P group will, a finite P group will have its order a power of that prime number, some power of that prime number. Right. We call on option 2. If order of G is equal to P to the power of 6, well, it is a power of P. Therefore, G is a P group, finite P group. Then G has at least 5 normal subgroups. Option 4. There exists a group capital G with its order P power 6 such that G has exactly 6 normal subgroups. Is it so? What is true and what is not true? For this, we call on a theorem. This is the theorem from a book, Dummett and Foote, and I will tell you where it is. This is the theorem what you have to recall. Let P be a prime and capital P be a group of order P to the power of A, and A greater than or equal to 1 is a finite P group. Then P has, capital P has normal subgroups of order P to the power of B for every B belongs to 0, 1, 2, 3 up to A. That means P has normal subgroups of order P power 0, P power 1, P power 2 and P power A. So many. So this is the theorem that appears as theorem 1 in the book entitled Abstract Algebra by Dummett and Foote, and which is a very important book for all the aspirants of CSIR NET examination. And this theorem appears on page 188. And this theorem otherwise can also be proved using the proof by induction. Agreed. But this theorem, honestly speaking, is not known to many. Agreed. So use this theorem now. So now by this theorem, order of G is P to the power of 6 means G is a P group, and G has normal subgroups of order P power 0, P power 1, P square, P cube, P power 4, P power 5 and P power 6. How many? 7 normal subgroups. So the G has at least 7 normal subgroups. So our option 2 says G has at least 5 normal subgroups. Therefore, option 2 is true. And there exists some group G with the order of G is P to the power of 6 such that G has exactly 6 normal subgroups. Once it has order of G is P to the power of 6, then it will have at least 7 normal subgroups. So there is no group G with its order P to the power of 6 which has exactly 6 normal subgroups. Once it has its order P to the power of 6, it will have at least 7 normal subgroups. Therefore, option 4 is not true. So therefore, option 3 is true and option 4 is false, not true. And we have to find out that statement out of the given 4 statements, that statement which is false. So we have got the false statement, that is the statement that is given in option 4. Therefore, the answer to this question is option 4. So that's all for this question. But however, I will show you how the other options, the other 2 options are not true. We continue in the next slide. Right. Option 1. If order of G is P to the power of 6, then G has a subgroup of index P square. So whenever the order is P to the power of 6, then G has a subgroup of index P square. That means it has a subgroup H, the distinct subgroups, the distinct cosets of that subgroup is P square. That is the index. Anyway, let's recall Sylow's first theorem. Let G be a finite group, P is a prime number. If P to the power of K divides order of G, then G has at least one subgroup of order P to the power of K. Right. Go to the order of G is P to the power of 6. Now P power 4 divides P to the power of 6 by Sylow's first theorem. G has a subgroup, let's call it as H, of order P4, P power 4. Then what is the index of H in G? Because G is a finite group, the index of H in G is the order of G by order of H. Order of G is P to the power of 6 by order of H is P to the power of 4. Therefore, the index is P power 6 by P power 4 is P square. So that's the result. Yes, this is true. Now p power 4 divides p power 6 by Sylow's first theorem, G as a subgroup. Let's call it as H of order p to the power of 4. Then the index of H in G is the order of G by order of H, because G is a finite group, and that is equal to p to the power of 6 by p to the power of 4, that is p square. So G has a subgroup of index p square. So option 1 is true. Right. Let's move to the next option, that is option 3. The center of G can be infinite. Here I have written can in red color. Can means there is a group G. There is a group G with this property whose center is infinite. So that means you look for an example. Can means, there is an example in which this happens. Because the center of G is infinite, the group G itself is an infinite set. That means you have to talk about infinite P group. So consider G is equal to power set of the set of natural numbers. Power set of natural numbers means set of all subsets of the natural numbers. It is clearly infinite, and it is a group under delta. Delta is the symmetric difference. How symmetric difference is defined? A, B belongs to power set of S. A delta B is equal to A union B minus A intersection B. So under this delta symmetric difference, it forms a infinite abelian group. It's an abelian group. And what is its identity? Empty set is identity, is the identity, and every subset of power set of n is its own inverse. Those are the properties of the power set of n under the symmetric difference delta. Now, for each A belongs to power set of n, we have A square is equal to A delta A is equal to A union A minus A intersection A. That is A minus A is empty set. Here empty set is the identity. That is A power 2 power 1 is 5. So that means 2 is the prime number. So here it satisfies the above property. That is for each G belongs to G, there exists an n belongs to n such that G power P power n is the identity. So here P is 2, n is 1. N is 1. And the 1 is, the identity is 5. So this is therefore it satisfies the above property, and it is an infinite abelian group. And what is its center? The center of an abelian group is itself. Now the center of G is G because G is an abelian group, and where G is infinite, therefore the center of G is infinite. So therefore there is an example where it satisfies the given property, a P group, infinite P group, and whose center can be infinite. Therefore, thus the center of G is infinite. So the statement what is given, that center of G can be infinite, is true. Is true. Therefore, option 3 is true. Right. Now summarizing all the options, the answer to this question, we have already seen this, that is option 4. And that is the detailed discussion of the solution of the problem from the group theory, which is related to P groups, or in particular P groups of order P to the power of 6. It is not that easy, but it is a little difficult in the examination hall. I say that the problem is not that easy. I am sure that you have understood the solution of this problem. I thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. We will meet once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.